Hi, welcome to another edition of Calculus 3. We are going to talk about some iterated integral examples today. That's going to lay the groundwork for many of the things we are going to do from now on. So here I've chosen a few examples that we are going to do. The first two are just ordinary integrals. However, there are several variables in it. We are going to practice how to integrate these things without getting distracted by the presence of additional variables. Then problems C, D, and E are actually iterated integral. Iterated, you see there are here two integrals to do. Later on we have to deal with perhaps three integrals. So let's go ahead, get started with the very first one. Very first one, you see that we have a integral x squared y dy, and the limits of the integral are from 0 to radical 4 minus x squared. So let's go ahead and do that one. So we have problem A, 0 to radical 4 minus x squared y dy. So the variable of integration is y. This is indicated by our differential here. We are integrating with respect to y. The other quantities have to be considered constant during this operation. So antiderivative of y would be just y squared over 2. What's the role of this one? Is just a constant multiplier. So antiderivative is going to become x squared y squared over 2. So we are finding antiderivative of y with respect to y. The limits of the integral, meaning starting and ending value of y, are these two quantities. So that is what we're indicating here, 0 and radical 4 minus x squared. So one thing to remember, if you have a certain variable here, the limits do not have that variables in it, rather it's the other variable. So in this case we get x squared, and then when I replace y by radical 4 minus x squared, I have to square it, divide by 2, and second time around I'm replacing it by 0, so x squared times 0 squared over 2. Of course the second item is just 0, and we have x squared, and the radicand comes out and divided by 2, and that is our answer. Okay, so that was easy startup example. The second one, so we have problem B, radical from minus, we have 1 minus y squared in radical to 1 minus y squared. Now it's positive here, and the integrand is x squared plus y squared dx. So the variable of the integral is x. So antiderivative of x squared will be x cubed third. Antiderivative of y squared, remember y squared for us is a constant, so it's just going to be y squared x. Now our limits are going to be these values, expressions. They are going to replace x, so this quantity is going to be substituted for x. So what do we get? From here on it's just basic algebra we have to do. So that radical has to be cubed over 3, and then y squared, then that radical. Okay, so this is the starting value, and then we have to subtract what we have at the bottom values. To make sure we don't make a mistake with signs, just put all of that in one big bracket to be subtracted. And now I substitute. Another caution is when you have minus something, just wrap it in a parentheses and take care of the signs later on. So third, and then we have y squared, and x again is to be substituted with this expression. Now you see that this looks mightily like that, and if you pay attention, this minus, when you cube it, stays as a minus, times minus becomes plus, so this expression becomes just identical to that, and this minus times that minus also becomes a plus, and our expression becomes identical to this. So this whole thing is going to essentially double, so we get double of radical 1 minus y squared cubed over 3, and then y squared radical 1 minus y squared. Now this is some feature that you see in many integrals later on. Notice that this is an odd function in x, meaning the powers of x are odd, and then you are evaluating from negative something to positive something. In all these cases, exact same thing happens. So if you have an odd function and you calculate it between negative and positive, you just get the double of the first entry. So that sometimes helps us to simplify the process a little bit. You can leave this thing alone, or you can try to clean up some more. I take this thing and cube it, so I get the expression times radical of that expression over 3, and then y squared times the radical again. And now we say, well, the radical can be factored out to clean this up. Even though in this problem cleanup is not required, it's something that you want to get used to, because typically the problems have multiple steps that comes up later on, and to the extent that you can clean up, that's going to be to your advantage later on. So 3 1 minus y squared, and then plus 3y squared, all told. So I can take the 3 outside as well, and then I have radical, and then I have 1 plus 2y squared. So that is the end result of this calculation. So that was example 2 of we're still doing a single integral but multiple variables. Next, our first example for a real iterated integral. So this simply means we have 2 layers to handle. So one have 6x plus 5y cubed, and that is dx dy. So that is example 3 that we are doing here. Okay, the idea here is that, well, first you do the inner integral. So this is sometimes we refer to this as inner integration or inner integral, just like the 2 examples we have done. At the end of that stage, we are going to have something with y's in it, and then we have to do a second layer of integration, and the second layer will be exactly like what we had in calculus 1. So in that sense, nothing is going to be any different. So let's go about doing this thing. So outside integral stays put, innermost with respect to x, I'll have 3x squared plus 5y cubed. And what else do I need to write? I would like to invite everybody to do this thing on their own and come back and compare. So this is a constant at this level. When you integrate it, it becomes that constant times x, and then limits are from 0 to y, and then dy. So now with respect to these limits, we have 0 to 1, this becomes 3y squared. This becomes 5y to power of 4. At 0, this all becomes 0. That's all that is left, dy. And then this becomes y cubed, and this becomes y to power of 5. And then we're integrating from 0 to 1. It simply becomes 1 cubed and 1 to power of 5, and that becomes a 2. So That was a first example of an iterated integral we did. Next, let's go ahead and take a look at our, this was, I guess, problem C, and problem D. We have 0 to pi over 2, excuse me. So this was problem C. This is D, 0 to pi over 2, and then the rest of it was 0 to 2 cosine of theta r dr d theta. When you see r and theta, it typically refers to a situation in a polar coordinate. Some equation is given in polar coordinates and we are performing same kind of integration, maybe finding an area or something. But as far as double integral is concerned, it's exactly the same as before. It doesn't matter if you have x and y or you have a and b or whatever, it's the same thing. So the inner integral with respect to r, and limits are with respect to theta, and then outer integral will be with respect to theta. So what's the antiderivative of r? Well, that's going to be, so let's write 0 to pi over 2. Antiderivative of r is r squared over 2. The limits are 0 to 2 cosine of theta, then d theta. Next, excuse me, we put the limiting values. So 2 cosine theta squared over 2, and then at 0, when you plug 0 here, it becomes 0 squared over 2 d theta. So 2 squared over 2, that's just a 2, this is just 0. So all boils down to integral from 0 to pi over 2 of cosine square of theta d theta. Okay, now this is a basic integral from calculus 1. It requires either integration by parts or a trig identity. You might remember double angle identity or half angle identity, that cosine square of theta is 1 plus cosine of 2 theta over 2. So this comes under the context of double or half angle identity. This is 2 theta, why they call it double, or this is half of that, that's why they call it half angle. Either way, so that would be a fast way of handling this. 2 cosine squared, 2 times cosine squared will be 1 plus cosine of 2 theta, again 0 to pi over 2. Antiderivative of this with respect to now theta. So antiderivative of 1 is just theta. Antiderivative of cosine is sine of 2 theta over 2. Then we have to evaluate it at the two ends. At high end we have pi over 2, and this becomes sine of pi over 2. At 0, well, is 0, and sine of twice 0 over 2. Now again, one more item from trigonometry. Sine of pi is 0, and of course sine of 0 is 0. 0, of course 0. So we are left with pi over 2. That is our final answer. So pi shows up because it's really calculating the area of a circle or half a circle. Okay, next item is problem E, integral from 1 to 3 of integral from 0 to y of 4 over x squared plus y squared dx dy. So that is our last problem for today. Let's go ahead and see how we do this thing. Okay, for this inner integral we have to work a little bit harder than the previous cases. Let's see if you can go ahead. So here was our clue that you stare at that, perhaps erase everything else from your memory, go back and see what you remember from calculus 2, trig substitutions, or calculus 1, and how do you actually go ahead and integrate that. Well, trig substitution, this kind of expression shows up when you have a right triangle with sides x and y and you're calculating the hypotenuse. So let's go get some inspiration from that. So according to that approach, we take a right triangle, and that introduces this substitution theta for us. The hypotenuse, of course, by Pythagorean theorem is that. Now, in this context, tangent of theta is a ratio of opposite to adjacent. So x can be substituted with y tangent of theta. So that's our so this comes up under topic of trig substitution. If you want to go back in your text, take a look at it. Well, when you have a substitution, so x is going to be substituted by this new variable theta. So I would need to substitute dx as well. How about dx? Well, that's going to be y times the derivative of tangent, which is secant square, then d theta. Next, well, how about secant of theta itself? I need to substitute my denominator as well. Secant is a ratio of hypotenuse, which is this, by the adjacent. So that tells me my expression x squared plus y squared in radical can be replaced by y secant of theta, and since in the denominator I have the square of this expression, that's going to be, of course, y squared secant square of theta. Now I'm ready to make my substitution. So let me first maybe write it here. So I have the integral from 0 to y, these are constants, over 4 over x squared plus y squared dx. Now let's go substitute. Maybe we finish our indefinite integral, come back and then substitute everything else later on. So I'll have 4 over x squared plus y squared, that became y squared secant square of theta. Dx became y secant square of theta d theta. So that is the expression here. Y secant squared cancels out. I'll end up with just 4 over y d theta, and that these are constants for me, so it becomes 4 over y times theta, and plus a constant. Well, who's theta itself? We should have written that here. Theta is tangent inverse or arctangent of x over y. So this becomes 4 over y of arctangent of x over y. So if I have integral from 0 to y of 4 over x squared plus y squared dx. I forgot to put my constant here. That's going to be 4 over y of arctangent of x over y. Don't need to bother with that constant, of course, from 0 to y. So that y is replacing x. So I'll get 4 over y of arctangent of, that is y over y, minus 4 over y of arctangent of now 0 over y. Well, y over y is 1, arctangent of 1. One more thing we need to know from trigonometry. Arctangent of 1. What angle is it whose tangent is 1? It's of course pi over 4. So that's going to be 4 over y times pi over 4. And then 4 over y. And of course arctangent of 0. What angle is it whose tangent is 0? Well, it's just 0. So 4's cancel, and I have just pi over y. So it took a while for us to do the inner integral. The inner integral just became pi over y. So I have now left with just integral from 1 to 3 of pi over y dy. So the inner integral just became that. Well, pi is a constant. Integral of dy over y will be logarithm of absolute value of y, which is, now we are in positive territory. It's all positive, so logarithm of y between 1 and 3. Well, this becomes pi logarithm of 3 minus pi logarithm of 1. One more thing we need to remember from pre-calculus, which is what was logarithm of 1? That was, of course, 0. So final answer, pi logarithm of 3. That expression boils down to this in double or iterated integral boils down to pi logarithm of 3. This type of problems on WebAssign, more than likely it asks for an exact answer, or it just doesn't mention anything. In that case, you just enter that. If it asks you for so many decimal places, then you use your calculator to give approximate answer. Okay, so our last problem, a bit more involved than the previous ones, because we had the trig substitution, and then we took a bit longer to do this. Okay, until next lecture, good luck and God bless.